Dear students, today we will discuss Theorem 1.34, which is known as Lebesgue dominated convergence theorem. So this theorem states that suppose Fn is a sequence of complex measurable functions on x such that f of x equal to limit n tending to infinity fn of x exists for every x belongs to x, and if there is a function g in L1 mu such that mod fn of x which is less than or equal to g of x for n varies from 1 to 3 etc. and for all x belongs to x, then first we want to show that f belongs to L1 of mu, limit n tending to infinity integral over x mod fn minus f d mu equal to 0, and limit n tending to infinity integral over x fn d mu equal to integral over x f d mu. Okay, so first we want to show this f belongs to L1 of mu, then this one limit n tending to infinity integral over x mod fn minus f d mu equal to 0, and finally this, that is limit n tending to infinity integral over x fn d mu equal to integral over x f d mu. Okay, so this proof is very simple, that is f belongs to L1 mu is very trivial. Why? Because we know that the fn is a sequence of complex measurable functions. Okay, each fn are complex measurable functions. Okay, then their limit also measurable. Okay, and we know that modulus f of x which is less than or equal to g of x, this is for all x. Why we have this limit n tending to infinity fn of x is equal to f of x. Okay, and also mod fn of x, this which is less than or equal to g of x. So we take in limit of mod fn of x which is less than or equal to g of x. That means we have this mod f of x less than or equal to g of x. And by the monotonicity of integration, we have integral over this d mu which is equal to integral over this d mu. Okay, so we have g belongs to L1 of mu. So that means this integral is finite, and therefore integral over mod f d mu is finite. So this implies that f belongs to L1 of mu, this one. Okay, now look at the second result, that is limit n tending to infinity integral over x mod fn minus f d mu equal to 0. Okay, so for this we consider 2g minus mod fn minus f. Okay, then we have, this is a sequence of measurable functions. Okay, we have mod fn less than or equal to, okay, mod fn of x less than or equal to g of x, also mod f of x less than or equal to g of x. Then we have this. Okay, then if we take this to this side, then we have 2g minus mod fn minus f which is greater than or equal to 0. Okay, so we have this function, that is 2g minus mod fn minus f is a sequence of measurable function which is greater than or equal to 0, means we have a sequence of positive measurable function. Okay, we have a sequence of positive measurable function, that is this one 2g minus mod fn minus f. So we apply the Fatou's lemma to these functions. Okay, we apply Fatou's lemma to the sequence of this function, that is 2g minus mod fn minus f. Okay, so what is Fatou's lemma? Fatou's lemma says that integral of lim inf, which is less than or equal to lim inf of integral. Okay, here we want to apply Fatou's lemma to this function. Okay, so we have integral over x lim inf of the function 2g minus mod fn minus f d mu, which is less than or equal to lim inf of integral over x 2g minus mod fn minus f d mu. Okay, now we consider LHS. Since fn converges to f as n tending to infinity. Okay, so this means this term goes to 0. So our LHS become this 2g only, this only. Okay, now if we consider RHS, okay, so we have LHS equal to integral over x lim inf 2g d mu. Okay, now on RHS we have limit infimum integral over x 2g minus mod fn minus f d mu. So we can split this RHS as integral over x 2g d mu. Okay, my plus lim inf integral over x minus mod fn minus f d mu. We can take minus outside the integral, so this implies integral over x 2g d mu plus lim inf of minus integral over x mod fn minus f d mu. Okay, now we use the result, that is, if suppose we have an greater than or equal to 0, then lim inf minus an, which is equal to minus lim sub an. So we use this. Okay, so here we have lim infim minus of this becomes, so this implies integral over x 2g d mu, okay, minus lim sub integral over x mod fn minus f d mu. Okay, so we have what is LHS, integral over x lim inf 2g d mu. So we have integral over x 2g d mu, which is less than or equal to integral over x 2g d mu minus lim sub integral over x mod fn minus f d mu. Okay, we know that g belongs to L1 mu, so that means this quantity is finite. Okay, this also finite. Okay, so we can cancel these terms. Okay, so this implies on LHS we have 0. So 0 less than or equal to minus lim sup integral over x mod fn minus f d mu. Okay, here we have, this is a positive quantity. Okay, and the minus of this positive quantity means which is negative. So we have, so this, from this it is clear that lim sup integral over x mod fn minus f d mu equal to 0. Okay, so this means the limit itself 0. Okay, that is limit n tending to infinity integral over x fn minus f d mu equal to 0. That's what we want. So we have this limit n tending to infinity integral over x mod fn minus f d mu equal to 0. Okay, now the last one, that is limit n tending to infinity integral over x fn d mu equal to integral over x f d mu. Okay, so we have proved this one. Okay, now we have consider this modulus, that is integral over x fn d mu minus integral over x f d mu, taking whole modulus, which is equal to, since integrals are linear, so we can write integral over x fn minus f d mu. Okay, so which is less than or equal to integral over x mod fn minus f d mu. Why? Because by using, we have already proved an inequality in theorem 1.33. Okay, we can write this as like this, that is integral over x which is less than or equal to integral over x mod fn minus f d mu, and this converges to 0 as n tending to infinity. Okay, so that means this LHS is converges to 0 as n tending to infinity. That means we have limit n tending to infinity integral over x fn d mu equal to integral over x f d mu. Okay, so this completes the proof. Okay, what is this conclusion? We can interchange limit and integral. What is this? This is equal to integral over x limit n tending to infinity fn d mu. Okay, that means in limit n tending to infinity integral over x fn d mu can be written as integral over x limit n tending to fn mu. Here we are interchanging limit and integration. Okay, so this completes the proof of theorem 1.34, that is Lebesgue dominated convergence theorem. Okay, thank you.